Hi, my name is Saachi Jain, and I'm going to talk about our work on deriving spectral lower bounds on the I/O complexity of arbitrary computation graphs. Many important applications are bottlenecked not by processing speed, but by I/O, the speed to transfer data between hierarchies of memory. There's thus considerable interest in designing I/O efficient algorithms and in understanding I/O lower bounds. We can describe any arbitrary computation via a computation graph. For example, here's a computation graph of a dot product. In a computation graph, each vertex represents a single operation. The parents of the vertex indicate operands for that operation. We assume a two-level memory architecture with a fixed amount of fast memory, M, and infinite slow memory. I/O is incurred when transferring data between fast and slow memory. Here we assume that when an operand is being computed, its parents have to exist in fast memory. The I/O cost of a computation graph is thus dependent on the order in which the vertices are evaluated. For the same computation graph, evaluating the graph with an efficient evaluation order can dramatically reduce I/O costs. A simple example of this is traditional matrix multiplication. In a standard iterative algorithm, assuming that m is less than n, when we iterate over the rows of the first matrix and the columns of the second, we're going to incur a cache miss on every operation, since the input data is going to be evicted from fast memory by the time it's needed again. On the same computation graph, however, if we divide our matrix into submatrices of size square root of m by square root of m, and sum the intermediate outputs, we can leverage fast memory much more appropriately and divide our I/O costs by square root of m by taking advantage of cache hits. Computation of lower bounds on I/O is typically very task-specific. We identify some specific property of the computation graph for a task via manual inspection to derive an I/O lower bound for that task. Analysis of this type is relatively straightforward for structured computations, such as naive matrix multiplication. However, many computation graphs are far more complex and heterogeneous in structure. These graphs are typically very difficult to analyze via standard methods like path routing and 2S partitions. In this paper, we answer the question of deriving an automatic procedure for computing lower bounds given any arbitrary graph, no matter how large or complicated. First, let's briefly cover notation. Let our input computation graph be G with n vertices. An evaluation order can be represented as an n by n permutation matrix. Valid evaluation orders must be topological on G. A child cannot be evaluated before its parent because the parents are the operands to the child's operation. We assume that when a vertex is computed, the parents of the vertex must be loaded into fast memory. We don't specify an eviction policy, though. Our lower bound thus applies to all eviction strategies. In this paper, we count non-trivial I/O. We do not directly include the cost of reading inputs or writing outputs. Instead, we assume that inputs can be read from the user directly into fast memory, and outputs are reported to the user immediately as they're computed. However, if an input is evicted from fast memory and is still needed elsewhere in the computation graph, it has to be written to slow memory and then read again. Let J of x be the non-trivial I/O incurred by x. We seek a bound on J star, the lowest I/O cost of any evaluation order on the graph G. We frame this problem in a manner similar to Ballard et al.'s approach in 2013. For any evaluation x on G, we can choose a partition P that divides the vertices V into disjoint subsets of vertices, so that each segment S in P is contiguously ordered by x. P thus defines breakpoints on x. For one segment S in a partition P, let R sub S be the vertices not in S with an edge going into S, and let W sub S be the vertices in S with an edge going outside of S. To evaluate the nodes in S, the vertices in R sub S must be read into fast memory, or otherwise they were already in fast memory before beginning computation of S. Similarly, the vertices in W sub S are freshly computed and are needed elsewhere in the evaluation graph. Thus, they must be written out to slow memory or left in fast memory at the end of S. Since fast memory's size is only m, at least R plus W minus 2m IOs are going to be incurred by evaluating the nodes in S. Summing over all S in the partition, Ballard et al. Derived this bound for an evaluation of X. However, the tricky part lies in evaluating the sizes of R sub S and W sub S. In Ballard et al., they examined the recursive structure of the Strassen algorithm to derive a lower bound for that specific task. They set the size of each segment to Q nodes. They then find a bound on the size of R sub S and W sub S, where S can be any subset of the graph of size Q. They then just multiply that number by n over Q to get a lower bound. This approach has a couple of issues. Firstly, it requires manually inspecting this graph, which is hard for more complicated graphs. Secondly, they generate a bound by finding the I/O cost for any Q-size subset of the graph. For a graph that has sections with high I/O and sections with low I/O, this cost would ignore the I/O intensive regions, resulting in a relatively loose bound. Instead, we seek an automated method that will take into account all nodes of the graph. Note that here we care about the node partition. We first simplify this lemma by relating this node partition to the edge partition, or in other words, the edges that cross S, by assigning each edge a weight dependent on the out degree of the source node. We can then derive this bound for the optimal I/O by maximizing over all possible partitions given in order. Intuitively, this equation means that an adversary picks some evaluation order on X on G. We then pick a hard partition P on X to maximize the I/O incurred. Any partition is going to create a lower bound. To keep things simple, we're just going to pick the partition which divides up the evaluation order X into k segments of n over k vertices each. We now tie in the graph Laplacian. The Laplacian of a graph is the degree matrix minus the adjacency matrix. It has a very natural connection to edge boundaries. If a vector x is a one-hot encoding of a subset of vertices S, then x transpose Lx will give you the size of the edge boundary of S. Thus, using the graph Laplacian, in our paper, we bound the equation from the last slide by the solution to the following quadratic assignment problem. Here, x is our optimization variable and is the evaluation order, constrained to be topological on G. L is the graph Laplacian, and W is a block diagonal matrix with k blocks of 1s of size n over k each. To find a bound on the solution to this problem, we relax this topological constraint and just constrain x to be orthogonal. The solution to the relaxed quadratic problem then simply involves summing the lowest k eigenvalues of the graph Laplacian, allowing us to bound the optimal I/O. This approach is very easy to compute. Any value of k is going to give us lower bound, and finding k eigenvalues takes O of kn squared time using power iteration. To find all the eigenvalues would take O of n cubed. However, in practice, the optimal k is usually much smaller than n. This method can further be computed for any arbitrary graph, and can result in closed-form bounds for graphs with known spectra. This bound also lends itself naturally to a parallel bound. Instead of the two-level memory hierarchy, imagine that we instead split the graph G on P processors, each with fast memory M. We count I/O as the communication between processors. Then the I/O cost actually divides very neatly by P. Intuitively, the proof is as follows. Each processor is going to evaluate a subset of the vertices in the graph. Given the optimal evaluation order X, we can define P sub-evaluation orders, where each sub-evaluation order indicates the evaluation order of that processor on its own vertex set. Since memory is local to each processor, we can use the same graph partitioning machinery as we used in the previous theorem, and just use it per processor. There's one processor that is going to evaluate at least n over p nodes, so we can just partition into kp parts instead of k parts, and sum the k sections with the lowest I/O cost. That processor must incur at least as much I/O as this sum. Using the same spectral machinery, we then arrive at this parallel theorem. In the next section, we're going to briefly discuss some results using this theorem to find closed-form spectral bounds for graphs where we already know the Laplacian spectra. First, consider the Bellman-Held-Karp algorithm for the traveling salesman problem. This is the traditional dynamic programming approach. The algorithm solves for the optimal path visiting a subset of the cities by leveraging the computed optimal paths through adjacent subsets with one fewer city. The computation graph can be formulated as a Boolean hypercube, where each node is a possible state of which cities have been visited. A hypercube has very well-defined Laplacian spectra and allows us to derive this bound for the optimal I/O, which scales with 2 to the L divided by L for an L-city TSP. We further derive a closed-form bound via this approach for the 2 to the L point fast Fourier transform. We derive a novel result for the Laplacian spectra and their multiplicity for the unwrapped butterfly graph. We use this result to derive a lower bound on the I/O using our spectral method. This bound is only a factor of 1 over log base 2m off from the provably tight bound, which was computed via manual inspection through S partitions. Finally, we empirically evaluate our bounds on 4 common computation graphs: the fast Fourier transform, naive matrix multiplication, Strassen multiplication, and Bellman-Held-Karp. We evaluate against a baseline, the convex min-cut method, which to our knowledge is the only previously published tractable method for creating automatic lower bounds. This method is relatively expensive though, as its runtime explodes for very large graph at O of n to the 5th, where n is the number of vertices. We also plot against the graph term for published bounds to characterize asymptotic growth. For these 4 graphs, we examine graph behavior for varying graph sizes and varying m. We find that our method is significantly tighter than the convex min-cut method and scales well both with the graph size and cache size. In particular, our method can deal with heavily heterogeneous graphs like naive matrix multiplication, while the convex min-cut method completely falls apart. Moreover, we find that our bounds roughly match the analytical growth of the published bounds, as the I/O versus the published bound is roughly linear for all 4 graphs. Finally, we note that our bound does not significantly degrade with m and can thus be computed for large memory sizes. In total, we introduce a new paradigm for finding lower bounds on the I/O of computation graphs using the spectra of the graph Laplacian. This method can be computed efficiently for any graph and can provide new closed-form bounds for graphs with known spectra.